Hello Intertubers and welcome to the first Geeky interlude. So this one is about spaceship journey time, specifically the journey in normal space, after you pop out of hyperspace and before you get to your destination. So we start with a maths problem, which is very familiar to anyone who's played this game. You have a spaceship which starts at a distance d from its target, because it's just popped out of hyperspace. The spaceship is stationary relative to its destination. Well, more or less. You do actually have some speed when you pop out of hyperspace, but it's so small that it's not going to matter. And then this is what the autopilot does: points the ship towards the target, and it accelerates with a forward acceleration F, and then later on it will decelerate with a backward acceleration B. So, big question: how long is this going to take? And we need to know that so we can predict whether we can take delivery missions or not. Simplifying assumptions, we're going to assume that space is empty, which it more or less is. And we're going to ignore gravity, because, gravity, even on Earth, when you're right next to it, is 1g. But if the spaceship is flinging itself around with accelerations like 25g, or even 10g, that's not going to matter very much. So before we do the real calculation, it's actually possible to learn something without doing any calculation at all. So in terms of units, acceleration equals distance over time squared. It's usually given in units like meters per second per second. So we have distances and accelerations, so the answer is going to be a time. How can we get a time? Well, there's no time in distance, there is some time in acceleration. So the only way to get it is going to be 1 over the square root of acceleration. That will give us a time, like the correct amount of time, times to the power 1. And unfortunately, a nuisance term made out of distance. How do we get rid of that? Well, we need some other square root of distance to multiply by to make it go away. So the formula will have to look something like that. And here's the clever part: we only have one distance as an input to the problem. So a formula must look something like that: square root of d divided by some acceleration made out of f and b. So time taken is proportional to the square root of d. And that already means you can you can get a rough and ready idea of how long things are going to take. If you know how far your ship takes to travel, say 10 AU, then it's going to take exactly twice that long to travel 40 AU, because 2 is the square root of 4. And anyway, time to do the calculation properly. So we want to know t, which I will split up into two values. Tf is the time spent accelerating forward, Tb time spent accelerating backward or braking. I mean, they both begin with b, so whatever. And then there's two equations. Once we split that t up, there's two equations that we can write down immediately. First one is the speed equation, which just tells us that if we go forwards, if we accelerate forwards for time tf and then accelerate backwards for time tb, we're stationary again, we get to 0. And then the distance equation, this part is the distance travelled by accelerating, this part the distance travelled by decelerating, must be equal to d. I think this is half acceleration times time squared. Pretty standard formula. The easiest way to derive it would probably be to notice that average speed has to be half acceleration times time. So what can we do with that? Well, you can simplify the distance equation slightly by multiplying it by 2, and then get rid of one of the variables by substituting in the speed equation. In this case, I've got rid of TB, and just a quick demonstration, if we go back to the speed equation, TB must be equal to FTF divided by B. So that explains that substitution. Once you've done that, then it's just a matter of collect the common factor, which is FTF, clean up that fraction, and then divide everything that isn't TF out, so we get an expression for TF squared. We could also do exactly the same thing for TB, and we get almost exactly the same answer. The only difference would be that B and F would be swapped over. Doesn't matter much in this denominator, but you can clearly see it here, F over B rather than B over F. Then, to get the total time, which is TB plus TF, just square root those things and add them together. And we have the common factor here and the uncommon stuff there. But we can do better than this. That thing on the right, well, we know how to add fractions, or at least I hope we do. And once we've added the fractions, we can certainly simplify squares of roots. And after that, well, we have a b plus f here, and we have a square root of f plus b on the denominator. They partially cancel, which will leave us with a relatively simple equation. And we can simplify it even further by breaking up the fraction. And that's the final answer, and it's surprisingly simple. Like, before I started this calculation, I expected something worse. Now, we know from the dimensional analysis that this square root of d had to be there, but this could have been almost anything so long as it was made up out of f and b. So I think I got off relatively lightly with that one. So how do we do this in practice then? We have one irritating problem, which is the units which the game gives us are not compatible. Acceleration is measured in g's, where 1g is Earth's gravity on the surface, which is 9.8 meters per second. D is in AUs. 1 AU is distance from Earth to the Sun. It's a really big number. And as for the answer, we probably want that in days. So if we now let T and D and R and F be numerical quantities with separate units, we get this equation. And then I can divide all that stuff out and pile it up on the right hand side. And I'll also take the opportunity to pick up this 2 and put that into the extra numerical term. So here we have 2 from up here. 1.496 times 10 to the 11, that's 1 AU in meters. It's a really big number. I think it takes light 8 minutes to get from the Sun to the Earth. Divide by G, 9.81 meters per second. And for compatible units, we can't use days, we have to use seconds. So 24 hours times 60 minutes times 60 for seconds. And you can work all this out with a calculator. And I did, and the number is surprisingly nice. It's about 2. I'm not going to round it down to 2 because the purpose of this is, to create estimates for whether we can deliver stuff or not on time. So giving a time that's too low is just about the worst thing you can do here. Still, it's so close that you won't be far off if you use 2. So now we can get to some examples. First one is how different ships would perform, because different ships have very different values for the forward thrust and reverse thrust. So first of all, the classic, the ship we start with, 25 G's forward thrust, 10 G's reverse thrust. And time is 2.39 days. And my personal rule of thumb is I just call that 2.5. The reason for that is the autopilot is not perfectly efficient, but we'll see just how bad it is later. Next up, the Eagle Mark II. See, it seems that the Federation liked the Eagle fight design so much that they made their own version. And for some reason, they took out the reverse thrusters, which are very good at 10, and replaced them with some absolutely terrible 4G reverse thrusters. They did make the forward thrusters better, which is nice. However, doesn't really make up for this. And in fact, this time, 3.42 days, indicates that was a terrible design decision, and I don't know what they were thinking. I have actually seen in some copies of the manual this number is 14, not 4, which makes me wonder, maybe this ship was destroyed by a typo. Because 14 would have been reasonable. Next up, Eagle Mark III. This is the Empire's version of the Eagle. Now, it clearly beats out the Eagle Mark I in both forward and reverse thrust, so it's really not a huge surprise that it scores a very low time. 2.04 days. That's excellent, and that's the best you can do with the autopilot. You can, of course, not use the autopilot and accelerate until you're halfway there and then flip your ship around and use the main thrusters as a brake. That would be the sensible way to do it, but the autopilot doesn't do that. So, ship number 4 is the Falcon. This is the fastest ship in the game, if we only care about going forwards. In fact, we shouldn't only care about going forwards. This is slower than the Eagle Mark I. Not by a lot, but it shows us that even the loss of 1G in the reverse thrust, it is doing more damage than is fixed by gaining 5G here. So it turns out that the smaller number is the much more significant one. Next up, Cobra Mark III, an iconic ship that many people like. In fact, it might be the best ship in the game, at least for fighting purposes. With that said, it's a little bit slower than the Eagles, with 20 forward thrust and 7 reverse thrust. But it still pulls in a respectable time, and it's better than the stupid Eagle Mark II, of course. Next up, Imperial Courier. This ship is the largest ship that can reasonably claim to be fast. It's a pretty big ship, weighs in at about 500 tons, and to have thrusters this good on such a big ship is pretty impressive. So 16 Gs forward and 6 Gs backwards. That's okay. That'll give you a 3-day time to fly through a normal system. And then finally, the slow ships. Starting with the Anaconda, there's a lot of very big and slow ships that all have the same statistics. 6 Gs forward, 3 Gs reverse. That's pretty pitiful, which means they'll take 4.5 days. So that makes some urgent delivery missions, particularly the federal military and imperial naval missions, makes those missions difficult. Of course, you probably don't care about delivery missions if you can carry as much cargo as an Anaconda has. These are the really gigantic ships with cavernous cargo bays that can haul hundreds of materials around, hundreds of tons of stuff around. You often find that they completely buy out all the trade goods in a starport. Next example, distances. Suppose we have this time the ship's always going to be the same, an Eagle Mark I, but D can be drastically different. Normal system, well, we've seen that calculation before. T equals 2.39 days. Next up, Achenar. This is the capital of the Empire, so there's often reasons to go there, like missions or trade, because you can make a lot of money because the capital of the Empire is a very rich and interesting planet. Also, you can buy any ship upgrade in the game there. So I often find myself going to Achenar for upgrades. But that 55 is kind of annoying. It means we take over twice as long to get to Achenar as 5.61 days. It's not that bad, but it's a little bit annoying and can affect Imperial Navy missions. Next up, 36 Ophiuchi. That's a system that you'll often go through when passing from the Federation to the Empire. 77 AU is a fairly substantial distance. And, well, here's a quick rule of thumb. Assuming we know this distance, then all we have to do is multiply it by the square root of 77 over 10. So square root of 7.7 is, well, it's more than 2 and less than 3. And a bit closer to 3, I think so. If we multiply this by 2 and a bit, then we're going to get like 6 or 7, something like that. 6.63 days. So that's reasonable. It's probably faster to dock at this place than it is to hyperspace again and spend 2.39 days going to the next system, but it's pretty close. I would like to skip this system if at all possible. Next up, Sea Greece. Now we're getting to the really annoying systems. So 266 is about 26 times 10. And if I call that 25, then the square root is very easy, it's 5. So I expect this to take 5 times 2.39 days, which would be 12. Well, slightly less than 12, but then we need to care that this is slightly more than 250, so more than 12. 12.32 days. And at this point, that's kind of where I don't ever want to visit that system, or I'll go through it, but I'll just double jump through it rather than having to spend 12.32 days docking. Like, it's faster to hyperspace again. It's going to cost no more than 7 days, and then spend the 2.39 days docking at a reasonable system. And then finally, the most obnoxious system in the game, Alpha Centauri. Well, 963 is almost 100 times 10, so square root of that is 10. We'd expect the answer to be almost 10 times 2.39, so 23 and a bit days. Yeah. And that's really obnoxious. At this point, I'm not sure if it's possible to succeed on a delivery mission to Alpha Centauri, because you get, I think, 28 days to carry it out. But you're going to spend 23 days getting there, and if you spend more than 5 days hyperspacing there, you're screwed. So there just doesn't seem to be any reason to ever go to Alpha Centauri. And that would be the conclusion. Don't go for Alpha Centauri, and thank you for coming to my TED Talk. Only stupid people go to Alpha Centauri. So let's do that then. Remember, we expect a 23.45 day time. So let's see how that works. And best, I think, to go to the Mars in the Sol system. This is a really weird starting position, by the way. You start out with a ship that has a beam laser, of all things, and an interplanetary drive, but you're in a safe system, so you're actually incapable of jumping to any system where you'd need the beam laser. So what we have to do here, and this is kind of silly, ditch the beam laser, remove the interplanetary drive, fit a class 1 hyperdrive, load up on fuel. Remember that some of the fuel goes in the drive. And fit an autopilot. So that will be enough. I suppose we can remove the missiles. I certainly won't be needing them. I just wonder, auto refueler, is that a thing? Quite an extravagance, but I'll fit an auto refueler. And off we go to Alpha Centauri. So this is really just a sanity check. Alright. Music off. So it's 5th of January and 7 in the morning. If I'm right, and this will take 23.5 days, then I should arrive at my destination on the 28th of January, it's 23 plus 5, pretty late, sometime in the evening. And even at the maximum time acceleration, 10,000 times normal time, this will take a while. I have to sit through this, of course. You don't. Lucky you. So we're late, less than a day late, and the reason for that is the autopilot is not perfectly efficient. It allows itself a little bit of slop so that it can recover from its mistakes and so that it can counteract inconvenient gravitational effects. I'm going to let this dock, and I'm a little bit curious as to whether it's going to make it. This doesn't look good. Yeah, see that diagonal cross? That's the direction we're going in, and oh dear. Now wait, it's corrected itself. This might be a success after all. All you need to do is point the ship to the right. Come on, you stupid autopilot. Point ship to right. Oh, this is going to be so close. We might even clip the top. Alright, and I think that's the end of that. See you next time.